Okay. Good morning, afternoon, or evening, everybody. Welcome to the Discover NASA's ISS Lightning and Associated Validation Data from GOESR webinar. This is your host, Jennifer Brennan. It's 2 p.m. Eastern Time, so we're going to go ahead and get started here. What I'd like to do first is go over just a few logistics related to today's webinar. To ensure the best audio experience, participants have been placed in silent mode, but if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you'll find that located on the right-hand side of your screen. And this works like a chat. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earth Data YouTube channel within a few days of completion. And then once this has been completed, what I'll do is I'll send an email to all registrants with the recording links. As far as timing is concerned, today's webinar will be 1 hour long, with 45 minutes allocated to the presentation and live demonstration, and then an additional 15 minutes for the question and answer period. Once our speaker has finished with his presentation, we will transition to a final set of optional polling questions. And then what we do is we'll give these, a few minutes or so, and from there move directly into the Q&A period. Depending upon the volume of questions that are received today, we will extend the Q&A period an additional 15 minutes to 3:15 p.m. Eastern Time for those of you who may wish or able to stay on the line. What I'd like to do next is pull up today's agenda. So let's go ahead and pull that up. Might take a second here. All right, great. Today's speaker is Dr. Jeffrey Stano. He is the DAAC scientist at the NASA Global Hydrology Resource Center, or GHRC, Distributed Active Archive Center, or DAAC. He will begin today's webinar with an introduction to the GHRC DAAC and also an overview of today's topics. And then from there, we will transition to an overview of the International Space Station, ISS Lightning Imaging Sensor, or LISS, both from a lightning observations and applications perspective. He will provide you with information regarding available LISS data and present information on how to discover and access these data using GHRC's data search tool, which is called Hydro. Next, we will focus on a lightning risk assessment use case in Hindu Kush. And then finally, during the last segment of today's webinar, we will discuss the GOESR post-launch test field campaign and associated data products. With that, it is my pleasure to introduce today's speaker, Dr. Jeffrey Stano. Jeffrey?
Jennifer, thank you very much for the introduction. As we start here, let me get our screen set up on this side, and we'll be ready. You heard from Jennifer's introduction. We'll be talking about the International Space Station Lightning Imaging Sensor, as well as the release of some of the new observations from the GOESR post-launch test field campaign. Before I even get started from that point, I'd like to also kind of extend my thanks to everyone from the GHRC, as none of this happens without everyone else that is working here. So I'm the presenter, kind of showing everyone's work here. So I'd like to state that right now and thank my colleagues. So with that, let's get started. The first thing I want to quickly mention, we've already been discussing this so far, is the topics for today's presentation. I'll be looking at two specific holdings here at the Global Hydrology Resource Center. The first one, as we've mentioned, is the International Space Station Lightning Imaging Sensor, or ISS-LIS. And then also I'll kind of spend the last third of the presentation on the GOESR post-launch test field campaign. This is covering the support of two of the Earth observing instruments, the Advanced Baseline Imager, as well as the Geostationary Lightning Mapper, or GLM. What's very interesting is both of these have unique capabilities that help support the expanded use of lightning observations. And I'm really going to be excited to talk about that, particularly with some of my background with lightning research up to this point. Also, kind of a quick note in terms of what we're looking at so far is that the GOESR satellite, before it is launched, it has a letter indicator. So it's GOESR, and it's also the name of the entire series. Now that that satellite is operational, it is known as GOES-16. So GOESR, GOES-16 are essentially interchangeable. I'll try to be careful in terms of what I'm using as we go forward through here. Now, I want to start off with a quick overview of the Global Hydrology Resource Center DAAC Center. So first of all, I am the new DAAC scientist here at GHRC. I just joined in January. So it's been kind of a fun transition for me to kind of learn about the GHRC as well. My background prior to joining the GHRC was with the NASA Short-Term Prediction Research and Transition Center. I spent 11 years there, and in fact, they're co-located in the building here with us. So as just a quick change upstairs for me in my venue, so the commute didn't change too much. A lot of the work that I've been involved in has been applications research. Specifically, I've been working with lightning. So I focused a lot on lightning safety, severe weather decision support, and then I also spent nearly 3 years serving as the satellite liaison for the geostationary lightning mapper. So that was kind of an intermediary role for helping with the training, both on foundational and operational usage of the GLM, working with the National Weather Service. In my new role here at the GHRC as the DAX scientist, I'm helping lead the outreach, data management, and science background activities here. So looking at the available audience that we have, there's been a discussion about there might be some varying degrees of understanding of what do the various distributed active archive centers do. So I'd like to spend a couple of minutes focusing on that as we go ahead. So overall, the DAACs are part of NASA's Earth Observing System Data and Information System. As you see on the map to the right here, there's about a dozen of these located across the country. Overall, their role is to really kind of process, archive, and document various NASA data sets. This is focusing both on past data sets as well as current missions that are ongoing. A lot of the work that we're trying to do is to really try to find ways to help users, end users, researchers, developers, to have access to these types of data easily and efficiently. For the Global Hydrology Resource Center, or the GHRC, this serves as a collaboration between NASA and the University of Alabama in Huntsville. So for myself, I work with the university, working with the GHRC, supporting this NASA activity. Also, the GHRC is serving as what's called a Science Investigator-Led Processing Systems location, or a SIPS system. Essentially what this is trying to do is, again, further extend the mission of what the DAACs are trying to do to support end users. So instead of just simply providing you a web page where you get a download link and just pull the data, GHRC and various other DAACs and SIPS locations are helping to try to develop means and methods with which to educate end users on the types of data sets they're looking at. We're trying to make sure that end users know about any kind of quirks that might exist with the data, any data dropouts, as well as providing information in the form of microarticles and data recipes to help visualize and display these data. In terms of the vision of what are the DAACs doing, the GHRC subscribes to the NASA Earth Science Data Systems vision. In essence, we're trying to make sure that NASA's data are free and open, also to make sure that these are interactive, interoperable, and accessible for research and societal benefit. Again, that really just kind of is an extension of what I spoke about on the previous slide, which is aiming to make sure that these data are not just available on just a web page where you go and pull the data, but there is supporting information, supporting documentation, and a little bit of training about what these data sets are so that they're accessible to users to help them with their own research and operations. Now, the GHRC is known for a number of activities here. In particular, we're known for working with lightning data. So in that effort, we've been working to ingest, archive, and do product generation for a number of different data sets. We've started all the way back with some of the earliest space-based lightning observations from the optical transient detector that covered a range from about 1995 to 2000. And that's kind of continued all the way through the TRIM lightning imaging sensor, efforts with the GOESR geostationary lightning mapper in the post-launch test field campaign, which we'll talk about a little bit later, all the way into the International Space Station lightning imaging sensor. So some of the data sets that we have available, in addition to the raw data, you can actually pull some of the climatologies. So this image on the right-hand side, this is showing the lightning imaging sensor 0.1 degree, very high resolution, gridded full climatology. So this has been kind of designed to be a little bit eye-catching. The brightest colors you see are where the greatest densities of lightning are located. You can see this in Central Africa, also a little bit of the southeastern United States, obviously Central America, and we do see some regions that we'll be talking about later in the presentation. Also, we do have some precursor instruments to the operational optical transient detector and a number of ancillary ground data sets. The main issue with a number of these ground data sets are many of these are private networks. So we have access to them. They support various individual activities, but they're generally not as regularly available publicly as some of the other data sets that are available. Overall, the GHRC has been recognized as the National Lightning Archive, and we're continuing with that with some new missions and some new activities. In addition to working with the lightning data, GHRC also provides field campaign observations. And what's really exciting about this is that we've been involved with a number of these activities for many, many years. In particular, we focused with some of the hurricane science missions dating back to the 1990s. What happens here is because of that kind of period of time where we've been working with the principal investigators, working with these individual field campaigns over many years, we've been able to develop common procedures, consistent metadata, and making sure that the archival system is standardized across all of these field campaigns. So an individual who is interested in looking at some of this hurricane science can actually use multiple field campaigns to acquire the data that they're looking for. More recently, we've been focusing on the Global Precipitation Measurement Mission, or GPM, ground validation. This has been an airborne field campaign mission to do a lot of the validation work for the GPM satellite. We've been working at that. Many of those data sets are now published, and we're working on some updates to that as we speak. As I've been mentioning, one of the topics that we will have today is the GOESR post-launch test, and I'll talk about that towards the end of our presentation here. So for the next few minutes, what I'd like to kind of go over is working with the International Space Station Lightning Imaging Sensor. This is going to be hopefully kind of the bulk of our presentation today. I'll kind of focus on the post-launch test field campaign towards the very end here. Now, the first question you might ask is, why are lightning observations important? There are some individuals on the call here who have used lightning data, so you'll have a little bit of understanding here. But for those of you who have not had the chance to necessarily work with lightning observations, here's a couple of things that were really kind of important and why we want to work with lightning data. Overall, globally, we have upwards of about 45 flashes happening every single second. If that's anywhere on the face of the Earth, there are about 45 of these flashes. They can reach upwards of about 50,000 degrees. So this is very interesting for atmospheric chemistry, that those types of extreme temperatures do help generate different chemical components in the atmosphere. At the same time, too, about a third of these flashes actually reach the Earth's surface as a cloud-to-ground strike. That's going to be a very significant differentiation to talk about, is looking at the ability to observe these cloud-to-ground strikes versus the intracloud flashes. And we'll talk about that in the next couple of slides here. Also, another thing to kind of look at that's important for lightning observations is understanding where is lightning occurring? How far does it extend away from a thunderstorm? What's causing it to be generated? What's generated lightning? And if you see a thunderstorm, when will lightning stop being produced? The reason why we want to look at this is due to lightning safety. Conservatively, based on available observations and available data sets, approximately 24,000 people are killed globally due to lightning. On top of that, about 250,000 people are injured each year due to lightning. And unfortunately, these values are likely conservative, as we don't have good records across the entire Earth for every country, so this is something that we really want to try to work on and try to improve. But in addition to looking at lightning safety, there are many different things that we can look at in terms of making the use out of these lightning observations. We can look at geographic trends. Where does lightning occur versus land versus the ocean? Different parts of terrain. We can look at climatology. We can look at the seasonal differences. How are lightning characteristics changing over time? What's kind of interesting from a climatological standpoint is that you can use lightning data as a bit of a proxy for convective precipitation. So obviously a thunderstorm. If we can assume that a certain location, if they're having the same amount of precipitation year after year, but that type of precipitation is changing from a stratiform precipitation type to a convective precipitation type, that has an impact on numerous things. You might have to worry more about flooding, how your farming works, agricultural activities. So those are things we can look at from these year-to-year observations as well. Other physical processes, again, we can look down the list. There's electrical circuit, lightning physics, lightning behavior, how is it happening? We can look at trying to model lightning observations. Also, the science applications, this is where I've done a lot of my work, has been with fire weather management, weather forecasting. We can use this to kind of identify precursors to severe weather. And as we mentioned, also lightning safety and weather prediction. The image that we see through here, this is a tropical cyclone Banzi from 2015. And this is kind of interesting. I really like this one, as you see a single lightning flash occurring, the light's being emitted from the cloud top, and then also lighting up the eye of that particular hurricane. And this type of light, this light being emitted from cloud top, this is how the International Space Station lightning imager works. It's detecting that light being emitted from the lightning flash. So a question that I want to raise is, what is total lightning? And I mentioned this on the previous slide, this differentiation between cloud-to-ground flashes versus intracloud flashes. And this has kind of some interesting issues in terms of forecasting, identifying severity of thunderstorms, and overall just understanding lightning safety. So the terminology that we use is something called total lightning. This is the combined observation of cloud-to-ground and intracloud observations. Now, if we look over here to the left, this graph is showing about 31 thunderstorms, as you can see for this lower right image, over central Florida. This occurred during the warm season. There's really nothing significant about these particular thunderstorms. None of these were severe thunderstorms. They just occurred during the warm season. Generally, they were being driven by the sea breeze across east central Florida. Each bar indicates the total number of cloud-to-ground flashes that occurred with each one of those thunderstorms over the course of their life cycle. So at most, we're seeing maybe about 55, 60 cloud-to-ground flashes within one of these thunderstorms. Beyond that, everything else was under 50 cloud-to-ground strikes. Now, I've always liked this presentation, this part of the presentation. It's an older image, but I kind of like this as a bit of a crowd pleaser as you then look at the intercloud observations. When you see this, you look at all the other lightning that's occurring inside that thunderstorm. And all of the blue bars are indicating lightning flashes that never come to ground. This is important because a number of the available ground-based lightning networks that you can use and have access to generally can only observe cloud-to-ground lightning flashes. So we need other types of instruments to be able to identify where are these intracloud flashes occurring. What's even more fascinating, a very interesting outlier here is the Storm 23. This particular storm had no associated cloud-to-ground flashes, yet it was the most electrically active storm of the entire bunch, with over 200 flashes associated with it. Now that's definitely kind of an unusual case, but again, it signifies the importance of being able to observe total lightning, everything that's occurring in that thunderstorm. Now one quick reminder, the satellite instruments that we have available to us, that's both the International Space Station Lightning Imaging Sensor, Geostationary Lightning Mapper, and others, they can observe total lightning, but they cannot differentiate between cloud-to-ground and intracloud flashes. So there's always going to be that important component of being able to combine both the satellite and ground-based observations. Now physically, what is occurring? Why do we even care about total lightning beyond just being able to say, okay, sure, we've seen these intracloud flashes? Well, as a reminder, total lightning is the observation of both cloud-to-ground and intracloud lightning. Physically, what is generating lightning? The charging of a thunderstorm occurs in the mixed phase region. So you're looking for an updraft that's getting into a part of the thunderstorm where you have a combination of liquid water and ice crystals, hence the name the mixed phase region. When you look at this, if you get a larger, stronger, and more voluminous updraft, you're going to see more charging and therefore more lightning. And this is a nonlinear process. As that updraft gets stronger and more intense, you're going to see much more lightning associated with it. Also, with some of the instrumentation that we have now available to observe total lightning, you get to see this spatial extent, this image in the upper left here. Not only are you seeing kind of where the lightning is most intense, generally where the core of the thunderstorm is associated, and we can kind of see that with the associated radar imagery. This radar is taking place concurrently at the same time, but looking at about 6,100 meters aloft. So we're into the mixed phase region. So you get to see here that the lightning is serving as a proxy for the radar. Also, these white lines, this is the outline for Limestone County, Alabama. So this lightning that we're seeing through here, this is extending roughly on the order of about 50 kilometers. So the lightning is going very far away from that core of the thunderstorm. Currently, the record holder right now is a lightning flash that extended 321 kilometers. And currently in the new geostationary lightning mapper era, that is likely to be exceeded based on verification. Now, there are several advantages to working with these type of data. First, we know that the intracloud lightning often precedes the first cloud-to-ground strike. We can also use these data as a proxy for storm strength. We can monitor convective development, whether it's strengthening or weakening, This can be very important for aviation forecasters who are working out over the oceans, who may not have access to any other data sets other than satellite observations. If you see lightning that indicates that a thunderstorm is occurring, you likely don't want to route aircraft into that location. We can see the spatial extent for lightning safety. At the same time, too, these types of advantages, this is just simply for operational end users. We can also look at these data for atmospheric chemistry and other research. Now, let's talk about the International Space Station Lightning Imaging Sensor itself. The movie that you see going on in the lower right, this is basically the space station's view of thunderstorms as it's passing overhead. It sees various light flashes occurring as lightning happens. So what the lightning imaging sensor is doing is observing and detecting these emissions of light and letting us know where lightning flashes are occurring. We can see where the imaging sensor is located on the space station. And what's really interesting about the history of this instrument is this is actually the flight spare of the Tropical Rainfall Measuring Mission's lightning imaging sensor. So the Tropical Rainfall Measuring Mission launched in 1997, had a 17-year career giving us lightning observations from orbit. Now this flight spare essentially sat in storage for that entire time. And then finally by 2016, it was refurbished and it was sent to the International Space Station and began providing observations in 2017. The image in the upper right shows the TRIM-LIS field of view, kind of the colored region, which is showing the climatology. And the advantage of the International Space Station lightning imaging sensor is that it does have a larger north to south extent of the orbit. So we get a little bit more of the mid-latitudes to kind of extend that 17-year climatology from the TRIM lightning imaging sensor. Now let's talk about what we have available here at the GHRC DAAC. Currently we have two types of data available. The first one is a near real-time data set. This updates roughly every 2 minutes. This is a change from how the TRIM lightning imaging sensor used to work. That used to be kind of a fairly long delay between an observation and then reaching end users. Here, now we have close to a much more usable real-time or near real-time data set. At the same time, too, we have provisional, non-quality controlled science data. So what does that mean? There's still some issues in terms of the validation and improving some of the quality control. That is coming. But the data are still generally of high enough level for science observations right now. And we see the example off to the right. This is northeastern Australia, showing all of the lightning imaging sensor flash densities observed over January 2nd and 3rd in 2018. Now, one of the other holdings that we're planning to do here at the GHRC is releasing the validated quality control data. This is in collaboration with the science team, and we're working on improvements to the lightning imaging sensor science algorithm. This will provide several processing corrections. We'll be able to start reporting the radiance values, or how intense is the light coming back to the sensor. And overall, we're aiming for a June 2019 release. Now, there are a couple of ways to access these data. And at this point, I'm going to pause here real quick and go to a demo on our webpage. And Jennifer, I'm going to quickly ask you if you are able to see the webpage here from the GHRC.
Yes, I am.
Okay, excellent. Thank you, Jennifer. So from what I have here, I've loaded up from the GHRC homepage. So if you're looking to kind of access these data, you can come to our main page. And the first thing I would direct you to look at is our Find Data. So we'll click on the Find Data icon through here. And this will take you to the Hydrology Data Search Tool, or Hydro. Essentially, this is GHRC's local tool to kind of search and explore for data sets within our holdings. There's a couple of ways you can look at this, but probably one of the easiest if you're looking for the International Space Station. So we can scroll down on the page through here. You move over to the left, we can click on Keyword, and a number of things pop up. And the first thing we'll look at is atmospheric electricity. Now you see on the right-hand side a number of things pop up through here. Since we've just recently published some data from the GOESR post-launch test, many of those lightning data sets are popping up right now. So we want to look at the International Space Station, so we'll go back over to the left, click on Platform, and we don't see it at the moment, so I'll click on View More. I'll scroll down, and we see ISS for the International Space Station. I'll click on that and scroll back up to the top of the page, and that brings us our 4 International Space Station data sets. In particular, I want to look at the non-quality controlled lightning imaging sensor provisional science data. So I'll click on that, and that will bring us to a new page. Essentially, this is the landing page in Hydro to show where we can get access to these data. You'll find a number of pieces of information through here. A quick summary of the data sets. the citation to use when you're working with these data, and also you'll finally get to the download link. And I'll show that in just a moment. Well, we can scroll down through here. We'll talk about the instrument, field of view. We'll see a graphic showing the field of view on the right, but also a number of pieces of information. We can look at a sample image. That'll pop up a new screen through here so we can see all the ascending and descending passes. We can also look at the micro article. This will kind of show you details about what is lightning, the importance of lightning, look at the International Space Station imager. And then lastly, probably what's going to be most useful at the moment is also the user guide. As I click on this and that pulls up a PDF, this will show all of the information about the International Space Station Lightning Imaging Sensor, citations, and details about the data set. At the same time, too, I can go back to our home page. We can also look under Measurements and Atmospheric Electricity. And that will bring us to our Lightning webpage as well. And from there, you can look at data set information and look at the International Space Station Lightning Imaging Sensor data. That'll bring you up to another landing page showing you some nice summaries of data. And then we can look down to the page to download observations and also look at some of the quality control or non-quality controlled browse images. So if we look at near real time right now, I'll scroll down, and we see the current swath from the ISS LIS is over kind of Asia right now, and there are no observations associated with that. So with that, I'll kind of move back to our presentation through here. And I will then move on to our next page. One of the other pieces of information that are available to end users are data recipes. So this is an opportunity to help end users access and use data available to end users to look at these data. So it's a way to observe and manipulate these observations. So instead of just kind of looking at the various data and just kind of leaving users on their own to look at these things, this is code both in Python and for ArcGIS to make it so that end users can kind of have an easier path at trying to manipulate and operate with these data. Now, for the next couple of minutes here, I want to drop into more of a conversation of some of the applications work that we've done with the International Space Station Lightning Imaging Sensor. This particular example came through a combined project with the GHRC and the NASA Develop project through the Applied Sciences Group. In addition, this is working with the NASA Severe Center as well as the meteorological agencies in Nepal and Bangladesh. So overall, the mission of this project was to try to integrate these NASA observations to understand the lightning risk and exposure in the Hindu Kush region. And so I'm presenting work from a couple of our colleagues and students here at the GHRC, and so with thanks to them, kind of move through some of these objectives through here. Overall, the idea has been to kind of aid partners in their emergency management and to help identify vulnerable areas, not just with frequent lightning, but where there might be vulnerabilities due to socioeconomic reasons as well. Now, at the very bottom, you see a wide range of data sets that were available, from topography data, information about socioeconomic information, as well as population data sets. As you move forward with this, I'll direct your attention to the left. This is showing the climatology from 2001 through 2017. Now, there's there's 2 years that are missing, 2014 and 2015. That's primarily due to the fact that the TRIM-LIS instrument was no longer operating at this time, and then the International Space Station instrument had not launched at that point. What this is showing is all of the lightning climatology density over the entire period of record. Two main regions stand out, the western regions of Nepal, as well as this Sylhet region of Bangladesh. Here we're seeing flash densities on the order of about 20 to 44 flashes per square kilometer over the period of record. Now, I'll kind of direct your attention now to the right. We can now look at all of this on a year-by-year basis. And there's a kind of a good reason for doing that. In addition to just saying, where are all the lightning occurring over the entire period of record, how does that evolve on a year-to-year basis? And we do see that those two regions that were highlighted earlier typically stand out each and every year for where we're seeing lightning. Now, as we move forward, as we mentioned, we wanted to incorporate more than just the lightning densities. And there's a reason for that. It's great to know where all the lightning is occurring. It's very good to understand where is most active lightning occurring. However, we want to bring in more information about topography, the people who are living there, as well as other socioeconomic issues. And when we do that, that creates this image across Nepal and Bangladesh showing a lightning exposure risk map. Brightest colors are showing the highest exposure to risk versus the cooler colors. And you'll see that there are some regions that have high lightning activity, particularly central Bangladesh, that have lower exposure to risk. The risk is non-zero, but it's definitely lower than we see in this northeastern region. That's being driven by a couple of factors. First of all, yes, there is more lightning occurring in those regions. So if simply by having more lightning, you have more exposure to risk. At the same time, too, economically, the majority of the individuals living in this region are doing agricultural tasks. So they're living and working outdoors on a very regular basis. It's not, say, here in many parts of the United States where many people now work inside office buildings. These are individuals who are working day in and day out outdoors. On top of that, unfortunately, this region also is generally not the most affluent region. So the structures that are available for these individuals, even when a storm is present, are not the most effective at keeping people safe during a thunderstorm. So it's structures here that you see kind of say in the United States. You have plumbing, you have wiring, other structural features which essentially make the building more like a Faraday cage, more structurally sound to resist a lightning strike. So an individual inside is generally a bit safer than in some of these regions. So the opportunity that was presented with this project is that it provided the emergency managers in these communities where they have limited funds available to identify where are the most at-risk populations, where is the exposure to risk greatest, and that way they can start sending money, limited funding, to help those most at-risk populations. Similar projects that have occurred out in Central Africa, where they work to try to develop like a school building that has lightning suppression systems, lightning rods, and other things to make it a safe location for the population. Also at the same time, too, one of our students was looking at the lightning data in correlation to convective activity, and this is looking at the Spearmans rank correlation coefficient. When we look at this, we see that all the correlations are positive. So overall, not overly surprising. You need to have convective weather to see lightning generation. But we see on a month-by-month basis, those correlations are highest in March, April, and May. Typically, when you look at this in a climatological basis, this is the non-monsoon season or the pre-monsoon season. So typically in this pre-monsoon season, this is where you're going to have more thunderstorm activity. Once you start going into the monsoon season and the later months of the year, you're having more precipitation, but it's generally more stratiform, more consistent rain over a longer period of time, and it's generally not as convectively active. And then kind of to summarize the project here, overall the greatest lightning occurrence was in the western regions of Nepal and the Sylhet region of Bangladesh. Overall, the greatest lightning risk, looking at the exposure to risk, was in northern Bangladesh and that southern belt of Nepal. Also we had the average monthly correlations over the entire study area showing that positive correlation. Now there are a couple of limitations with this initial study. We didn't mention the aforementioned gap in the available lightning data. Also, a number of the ancillary data sets were not current or concurrent with one another. Our population data was only available from 2016. Socioeconomic information was only available in 2015. In spite of that, this has developed an excellent starting point for kind of looking at this lightning safety effort. And some future work with these types of projects are to try to expand this and get access to more of these socioeconomic and population information over the entire period of record. At the same time, too, with the lightning imaging sensor available now, we hope to kind of continue to extend this over a longer period of time. With that, I'd like to kind of wrap things up in the kind of the last 10 minutes or so here of the presentation, really talking about the GOESR, or GO16 now, post-launch test field campaign. So a quick background. The GOESR satellite and series is the first of 4 satellites in a new series of next-generation weather satellites launched by the United States. GOESR is both the name of the series as well as the first satellite in that series. That was launched on November 19th, 2016, and its sister satellite was launched in 2018 and was GOESR and is now known as GOES-17 in the western part, covering the western part of the United States. Overall, the satellite carries a number of instruments. Two of these are solar observing instruments. Another two are space weather instruments. But primarily for this presentation and for the holdings that we have here at the GHRC, we're looking at the Earth observing instruments. The first one is the Advanced Baseline Imager, or the ABI. What's really exciting about this is that this shows 3 times more data than what was previously available. This is done through the various channels that are available. The previous generation GOES imagery typically had 4 channels. Looking at the GOESR, the Advanced Baseline Imager, it now has 16 channels. There's better ways to interrogate the atmosphere, understand what is going on at multiple levels and different frequencies. There's 4 times better resolution. So a number of these instruments are getting down to, number of these channels are getting down to the half kilometer or 1 kilometer resolution. Infrared imagery on the previous satellite was at 4 kilometers. Now it's down to 2 kilometers. This really helps for looking at smaller features that were difficult to see previously. Also, the data are 5 times faster. So one of these ways to look at it, at times it took 10 to 15 minutes to get a single scan across the United States. Now we can look at that in 5 minutes. We can also do special other features, which are a mesoscale sector. So this is a 1,000 by 1,000 kilometer region that the satellite can direct its attention to. That can be updated every minute. Or, since it can do 2 of those sectors at the same time, you can overlap those 2 sectors, and with the visible imagery, you can get half-kilometer imagery every 30 seconds. Obviously, you have to get things, all those be aligned at the same time. Typically, you're not going to see that regularly, but again, it shows the capabilities and the advancements that have been made with the Advanced Baseline Imager. At the same time, too, there's the Geostationary Lightning Mapper, or the GLM. This is the first ever operational instrument of its type. Yes, we've been talking about the International Space Station Lightning Imaging Sensor. That's available, but that is in a low Earth orbit. As we saw that one animation, or that one movie from the ISS, you're kind of briefly over a point on the Earth. You can see the lightning that's occurring while this space station is overhead, and then it passes on. By being based on a geostationary platform, GOES-16, GOES-17, we're able to stare over almost the entire hemisphere that is being covered by the satellite and look at thunderstorms throughout the entire life cycle of these thunderstorms thanks to the GLM. So it's really kind of exciting and opens many new doors for some research opportunities as we go forward. Now, the field campaign itself, the effort was focused to validate the Advanced Baseline Imager and the Geostationary Lightning Mapper instruments from GOESR, now known as GOES-16. Part of that effort was to look at all the spectral radiance validations for the 16 channels from the ABI. So this was done by the NASA ER2, and you can see a number of these flights through here. They were taking this aircraft out over the ocean, the Sonoran Desert, Great Plains, over thunderstorms. They were looking to make sure that what the satellite was seeing was matching the instrumentation that the aircraft was carrying. Also, we were working to validate the GLM flash detections. So there was a couple of instruments specifically for detecting lightning that were available. Now, there are numerous observations throughout this field campaign in addition to the aircraft observations. We have surface-based lightning mapping arrays. These are generally kind of considered the gold star of lightning observations, where they can see intercloud and cloud-to-ground lightning. For the most part, they do have some support from other ground networks, but their main drawback is they have a very short range. Also, we have aircraft instruments with the lightning instrument package, serving much as an electric field mill, identifying where is the electric charge in the atmosphere, and also the Fly's Eye GLM simulator. In many ways, this is like a miniature GLM aboard the ER2, and where the GLM has a resolution of, say, 8 kilometer footprint, the Fly's Eye GLM can provide a 25 by 25 pixel array inside of one of those GLM pixels. So the effort there was that the Fly's Eye GLM simulator kind of worked to help identify how is lightning being distributed inside a single GLM pixel, and then how is GLM interpreting that. Also, while not part of the post-launch test field campaign explicitly, the ISS LIS was useful to kind of have some underpasses as well. Now, much like the International Space Station Lightning Imaging Sensor, we do have the ability to look at these data through the GHRC's Hydro tool. And again, I'm going to move us out of the presentation briefly and go back to our home page. Once again, we can go over to the home page for the GHRC, and I'll move us down to the Find Data location. As that loads, I'll want to show something a little bit differently from what we've done with the ISS LIS. What we can do here, this is the Post-Launch Test Field Campaign. So this is abbreviated PLT. So let's say you knew that already and you're able to kind of look for that. We can actually search the data set. I can just type in PLT, hit enter, and you see through there all the various data sets associated with the GOESR post-launch test are available. We'll look at the various ground networks. We'll look at the lightning instrument package. Excuse me. And once again, it'll take you to one of the landing pages where you can download the data, get access to the download, and pull these information, as well as browse images, how to get the data, some viewing some images, user guides as well. With that, I'll go back to our presentation. So currently, there are 9 data sets that have been published for the post-launch test, 7 lightning-related data sets. 7 of these are the ground-based lightning mapping arrays, and then 2 of them are aircraft-based instruments, the lightning instrument package that I mentioned, as well as the Fly's Eye GLM simulator. Currently, we're slowly working on the various ABI-based or the ABI validation instruments. We have already published one of those. That's the Scanning High-Resolution Interferometer Sounder. That was published on May 1st. And just kind of looking at some of the geostationary lightning mapper-related data sets, the initial part of the field campaign focused on the advanced baseline imager validation. The main part for the GLM, or the geostationary lightning mapper validation, that began in mid-April of 2017. The imagery to the right shows a couple of examples of the various data sets. This image through here that I'm cycling through, this is from the North Alabama Lightning Mapping Array, imagery provided by NASA Sport. And again, you see, again, that's spatial extensive lightning, very different feature from what you may see on the news, where they show a little lightning bolt on TV. That's just showing where a cloud-to-ground strike is occurring. Here we're seeing lightning flashes that are covering a wide region of area. This is all the lightning that was occurring in 2 minutes. Also, courtesy of Mason Quick, the PI for the FEGS, or the Fly's Eye GLM simulator. We see the various data sets available through here, as well as the lightning instrument package, the field mill information. Now, what's really interesting about the post-launch test data sets, this is really a unique opportunity for end users to pull multiple data sets together from aircraft, ground, and satellite-based observations. First of all, there are multiple lightning observation platforms. Normally, lightning data can be very difficult to get a hold of, and we now have multiple data sets that you can pull together and look at. Once you start combining this with the data that are available from the GLM and ABI on NOAA's CLASS system, you can really start kind of integrating all these various data sets together to look at some nice convective studies. Also, what's really nice for here at GHRC and other end users is that this is one of the first availabilities of lightning mapping arrays in some of our holdings. So we're really hoping to continue that work with some of the lightning mapping arrays to not just look at this small 3-month window of data, but eventually bring in their full period of record for end users to look at other lightning and convective-based studies. And with that, I'd like to thank everyone for attending here today. I'll once again thank Jennifer for her help in organizing this, and for my colleagues here at GHRC for all their help in the presentation.
Okay, thank you, Jeffrey. At this point, what we'll do is we'll transition to our final optional set of polling questions. And we'll give these questions about 3 minutes or so, and then from there we'll jump directly into the Q&A. And there are actually quite a few questions that have been posed so far, so we'll get started in just about 3 minutes. All right,
I will look forward to it.
All right, excellent. Okay, everybody, we're going to give these questions just another minute or so, and then we'll move to the Q&A session. Okay, with that, let's go ahead and transition to the Q&A session. And give me just one moment here to pull up our first question. So the first question that was asked has to do with, Jeffrey, could you describe the difference in processing and validation between the near real-time and standard ISS list products?
Yes, part of that on the near real-time versus the actual science level data is essentially you're trying to just kind of get the data out as quickly as possible so that end users can have access to the data as soon as it's available. So part of that is when you look at the image, and I'll kind of show, I'll go to our webpage to kind of help describe that better here. Sorry about that. As you go to the webpage through here, I'll go over to our measurements, atmospheric electricity, and go down to the ISS LIS data at this point. One thing we can look at, if we look at the near real-time browse image, you're just going to see one single granule of data. So this is showing 2 minutes worth of data from the ISS LIS. Whereas some of the more processed, the quality-controlled data, we look at that browse image, we can look at a single data.
You're not sharing your screen anymore, just so you know, because we're
oh, I'm sorry.
Yes.
Well, that would be difficult for you to see what I'm doing then.
Right.
Then what I will say, the main difference is with the near real time is that you're getting each individual granule of data from the ISS LIS basically as it's occurring, and so you don't see the entire orbit. Whereas with the non-real-time data, you can receive data in the full orbit or over a day times period. In terms of the processing, the near real-time, you're attempting to really just get the data out the door as quickly as possible. So you won't necessarily have as much of the full quality control goes into it. Obviously, making sure that you do have a flash, you filter out noise, things like that. But when you do kind of that post-analysis, you can do a little bit more quality control checks than on the near real-time.
Okay, great. Thank you. Our next question is, how can we differentiate intra-cloud and cloud-to-cloud lightning observations from ISS LIS?
So the question was intra-cloud and cloud-to-cloud, or cloud-to-ground?
Yes, that's right. How can we differentiate intra-cloud and cloud-to-cloud lightning observations from ISS LIS?
More than likely, that is likely not possible to identify the two between that. When we look at the data, you can do some additional processing. You can eventually plot you can map out the entire lightning flash. And so you can see flashes that go a large distance, 10, 20, 50 kilometers. Those are likely going to be more cloud-to-cloud versus a singular intra-cloud lightning flash. However, that's just kind of an inference at that point. Generally, intra-cloud is typically used as a catch-all for anything like that, either a intra-cloud, cloud-to-cloud, or cloud-to-air discharge. Basically anything that's not going to ground.
Okay, great, thank you. And then following up to that one, the user is asking about whether or not you can differentiate between intra-cloud and cloud-to-ground.
From the space
may be identified separately.
Oh, that's another excellent question. From a space-based perspective, generally the answer is no. Typically, it is going to see light emitted by the lightning flash, and it's generally not going to be able to tell you the difference between an intra-cloud versus a cloud-to-ground flash. I do know there's been some effort to try to see if they can tease out a signal between the two, looking at the radiance values that are emitted, but overall, there's no way to do that. That's why generally the space-based instruments are often used in conjunction with the various ground-based networks that can observe the individual cloud-to-ground flashes.
Okay, thank you, Jeffrey. And then the next question is, will the ISS list observations end this year? Just about 3 years of observation.
At this point, no. I believe there's some work right now to continue the mission for, I believe, another 2 years. And then from there, we'll have to wait and see what happens at that point, if there's space still available for the instrument or not. But we're looking at 2 more years of observation from ISS LIS.
Okay, great. Thank you. So the next question has to do with processing the data using Python. Let's see. To combine the ISS list, so it's really a combination comment versus question, okay?
Okay.
To combine the ISS list files, the available information in Python code is not clear, and please do update the complete and clear Python code for processing the data. There's really not a question in there.
No, well, that's excellent to have. I do appreciate that comment, as that's the type of feedback that we're looking for from our end users, and so I thank you for that comment.
All right, great. Thank you, Jeffrey. The next question is the Foothill of Himalayan experience more lightning flash, like you mentioned for Nepal, southern part? How can I relate the Wrapup effects?
Oh, the orographic effects.
Oh, excuse me, right. There's a correction later. Yes, the orographic effects. I missed the user had corrected the question later on. My apologies.
Oh, no, not a problem. And so could you state the question again? I apologize.
Yes, and so, okay, and the Foothill of Himalayan experience, is the Foothill of Himalayan experience more lightning flash, like you mentioned for Nepal, the southern part?
Yes.
And then how can I relate the orographic effects?
A lot of that, again, we can't show the screen right now, but if you go back to the presentation and look at the flash densities over particularly Nepal, you'll see a very stark boundary kind of over that central spine of Nepal. And essentially what you're having happen there is, as they mentioned, the orographics there, the moisture-laden air is coming up. It's coming up against the Himalayan mountains. It's being forced up, so you get that nice forcing to lift that moisture and that atmosphere up, and that's helping generate the thunderstorms through there. Once you get beyond the Himalayan mountains, going to that northern side of the Himalayas, you see there's very little lightning, if any, occurring beyond that point. And that's a twofold thing. One, you're beginning to descend on the northern side of the mountain, so obviously descent, you're not going to get convection out of that. But also the extreme height of the Himalayas, a lot of that moisture is raining out on the southern side, and by the time it gets over onto the northern side of the mountains, there's very little moisture to help drive any convection as well. So essentially that is, as the question was asking, the effects from the orographics.
Okay, great, thank you. All right, so the next question is, does cloud-to-cloud lightning increase over time? If so, does it indicate changes in cloud microphysics?
Another excellent question. A lot of that goes into some of the operational forecasting that are being done working with Total Lightning. When you look at some of this through here from an operational standpoint, being able to observe that intercloud lightning is very useful. What happens from there is we're looking for a feature called a lightning jump. And essentially that's some work that's been done here in Huntsville by a number of researchers where they're looking for a very rapid increase in lightning activity in a given thunderstorm. Generally, that's been serving as a precursor for a severe weather event. Typically, you need to have that total lightning observation or those intercloud, cloud-to-cloud components versus just the cloud-to-ground observations. Because typically that trend is not available or does not get observed in the cloud-to-ground only data sets. So yes, there's the lightning jump component. You can look for severe weather. Even without severe weather, if you see more lightning occurring, that's indicating that you have a stronger, more voluminous updraft, and so therefore it's a proxy for the strength of the thunderstorm. Lastly, going back to the change in the microphysics, yes, you can infer some of the microphysics through that as well. Part of that comes from the fact when you can look at the spatial extent. If you're looking at a young, active convection, a very strong thunderstorm updraft, it's a very heterogeneous electric field. It's very scattered. There's lots of different smaller pockets of electric charge, positive, negative, all over the place, and you'll get more flashes, but generally of a smaller total area. As the storm becomes more mature, your electric field is going to become more homogeneous, and that's when you start getting these very large stratiform lightning flashes, or as more colloquially known as anvil crawlers. And that's going to kind of show that that electric field is kind of become more homogeneous, and your microphysics are a little bit more similar across the entire area, allowing you to get those larger flashes.
Okay, thank you. The next question is the LMA data with GHRC, is it a kind of signal or image? And then there's some follow-up questions. So I guess the first question is the LMA data with GHRC?
Yes, currently there are 7 lightning mapping arrays at the GHRC. This is coming from a network in Toronto, North Georgia around Atlanta, North Alabama centered on Huntsville, Alabama. I think we have Oklahoma centered on kind of central Oklahoma, Kennedy Space Center, and another one near Boulder, Colorado, kind of the northern part of north central Colorado. With that being said, the data set only covers about 3 months of data, only the data from the GOESR post-launch test field campaign. We are looking to eventually work at least at first with the NASA-owned lightning mapping arrays to archive their entire period of record and not just this field campaign.
Okay.
And I believe there's a second question in there. And if I could, Jennifer,
yes.
If I could ask for a repeat, please.
Yes, there were actually several. Okay. So the first piece is the LMA data with GHRC. Is it a kind of signal or image? How many sensors are used for the lightning mapping array data? And then what is the range? So
okay, I'll go and
image. Oh, okay, so you got.
Oh, sorry, Jennifer.
No, go ahead.
Okay, I'll go in reverse order for you there. Generally, the range of these networks, at best, you're getting out to about 250 kilometers from the center of the network. When you're looking at these data, most of the research will stay within about 60 to 100 kilometers if you want to get the 3-dimensional component of these lightning data. You can go outwards to about 100 to 150 kilometers for very effective 2-dimensional observations. In terms of the number of sensors, that will vary by lightning mapping array. Typically, for a bare minimum, you need to have 6 sensors operating in a lightning mapping array to get viable science data. Most of these networks operate with more than 6, generally on the order of about 11 to 16 sensors. That way there's redundancy, and it also creates a larger baseline for the network so that you can kind of get a little bit more range out of the network. Typically, if you look at a storm that's advancing, say, west to east across a lightning mapping array, it will enter the field of view of the lightning mapping array. You'll see activity ramping up. That's just simply a detection efficiency issue, not just seeing ramp up in the thunderstorm. But as again, to that kind of that 150-kilometer range, that's when you're going to see a really good signal of the intensity of the lightning and not just a detection efficiency issue. I'll try that again. The last part of the question is talking about what is the lightning mapping array data provided here at GHRC. These are typically ASCII files. I don't believe we have any. We might have a browse image or two, but generally these are ASCII files. And the lightning mapping array operates in what's called the very high frequency part of the spectrum. So we're looking at kind of like the 83 gigahertz range. In many ways, prior to the changeover to digital with television, it's operating in the old analog spectrum of television stations. And what you're seeing is the raw data that you observe are lightning mapping array sources. These are individual VHF observations of a lightning flash. In many ways, these are kind of corresponding to the stepped leaders, which are the individual pieces that make up an individual lightning flash. So once you get these data, you can pull in these data, and you can start reassembling these sources into flashes, and you can do the mapping from there.
Okay, great. Thank you. The next question, and I do want to note that we have now entered the extended Q&A period. So we'll go to 3:15. There'll be a hard cutoff at that point. And any questions that are not answered during the framework of this webinar will be forwarded along to our speaker, and he can follow up offline with you individually. So our next question is, what is the case of Florida/South Africa storms? I think they are not on high from sea level. So let's see. So can I say convection happens differently in various orography?
I believe that's a fair statement. I mean, what is going to be the initiation point of an individual thunderstorm? It will vary by region. You can have numerous things that can initiate a thunderstorm. Simply lift that's being forced by orographics, so mountain ranges, things like that. The central part of the United States, or the south central part, Texas, Oklahoma, you can have a dry line, that a gradient in water vapor, not water vapor, but a gradient in moisture can help initiate a thunderstorm. You go to Florida, that's sea breeze driven. So you have temperature pressure differences that generate the sea breeze, that can generate lift that can initiate a thunderstorm. So yes, there are going to be different mechanisms that will kind of kick off and initiate the thunderstorms throughout various parts of the world. Hopefully I answered that question accurately to the questioner's liking.
Okay, let's move on to the next question. For the lists and the OTD data for the years between 1997 to 2015, will the time series of these data files be available in a simple way, for example, as a single file?
I will have to double check on that. One quick thing with the OTD data, there will be data that go back all the way to 1995 as well, so we'll get 2 additional years through there. There are the annual climatologies that are available. I'm not sure if that's a single file at the moment. I think that's something I would have to follow up with the questioner offline.
Okay, great, thank you. And so the next question is, I know that lightning can occur in multiple colors. I have heard that the color of lightning has to do with how far away the observer is. Are we able to infer additional details or conclusions from the color of lightning?
I would say at this point, no. A lot of that comes down to atmospheric phenomena and features in the atmosphere. Yes, the statement from what the questioner is asking in terms of their range from the lightning, that can be an impact due to the fact that there's going to be more atmosphere between you and the source of the lightning. And that can be driven by any number of things. How much water is in between you and the lightning flash? How much dust is in the atmosphere? How much other particulate matter? And even the angle of the sun, your lighting conditions. But in terms of actually having an operational usage, no, there's not really anything used in types of color from there.
Okay, thanks. So, and I maybe perhaps missed the first part of this question, but there's a question here comparing, let's see, it's missing the question piece. Over the Himalayan region, max, the Cape location are different with respect to peak rain rate. What could the reason be for that? Why is there a difference when comparing the Himalayan region, it says max, Cape location? I hope I've captured this properly from this user.
I'm trying to see if I can kind of piece that one together here. I think that one's going back to that correlation image that we showed on one of the earlier slides. I think if it's possible, I think that might be a question that if the user can reach out to us, or if we can get their contact information, we can better address that question offline.
Okay, that sounds like a good idea. Let's see if there's additional clarification. Okay, the next question is, are you using any lightning mapping array validation in Asia or African continents?
Currently, no.
Continents? No. Okay.
Currently, no. There are no operational lightning mapping arrays in Asia or Africa. However, there is work over Lake Victoria in East Central Africa. That is, actually there's an ongoing campaign that GHRC is involved in right now. This is a collaboration with a number of entities, both the meteorological entities supporting the Lake Victoria region. I believe there's a little bit of World Meteorological Organization efforts involved, and also the private company called Earth Networks. While it is not a lightning mapping array, they do provide it's a ground-based network that can observe cloud-to-ground flashes and a percentage of the intercloud flashes as well. And so that is an effort that GHRC is involved in and helping try to better characterize lightning over Lake Victoria.
Okay, thank you for that explanation. Let's see here. Okay. A couple of participants have indicated that the question and answer section is very informative, so we're glad to hear that.
Oh, great. Thank you.
All right. Let's see. At this particular point in time, oh, excuse me, we do have another question. It's just come in. I was just getting ready to say there's not. GIS data was mentioned. Are there REST services available for maps that can provide real-time or the most up-to-date information?
Jennifer, I apologize. I missed the very opening part, and I was uncertain as to the question.
That's okay. GIS data was mentioned. Are there REST services available for maps that can provide real-time or the most up-to-date information?
Not yet, but there are definitely plans to do so. That's been one of the things that we've discussed internally due to the fact that a number of end users are proficient and prolific users of GIS data to kind of combine multiple data sets into one visualization. So that's definitely something we want to move towards.
Okay, thank you. All right, I'm just scanning the Q&A pod to determine whether or not there are additional questions. All right, any additional questions? All right, while we'll give this just another minute or so. In the meanwhile, I want to draw your attention to the fact that today's presentation, PowerPoint file, is available for download. You'll find that located in the file sharing pod in the lower right-hand corner of your screen. If you highlight that file, you will be prompted with an option to download the file. All right, and if there are no further questions at this time, I do not see any. What we will do is we will log off from the audio component and leave the virtual meeting space open an additional 10 minutes or so. For those of you who may be interested in downloading the presentation file, or you think of something after the fact, please feel free to enter that into the Q&A pod, and we will forward that log to our speaker. All right, any additional questions?
I'd like to take the moment here to, once again, Jennifer, thank you as well, and also thank you to all the participants for your questions. I've enjoyed it, and I'm glad it's been beneficial.
Okay. With that, I'd like to say thanks to everybody, and we hope to see you at an upcoming webinar. Actually, our next webinar